Okay, let's work through another example. So here we're going to work with an example of false positives in medical testing. So let's suppose that there's some disease and that the infection frequency in the population is 1%. And that you have some tests that can test whether or not you have this disease. And this test, so no test is perfect. So this test has a false negative rate of 20%. So in other words, it has an 80% success rate at detection. And it also has a false positive rate of 10%. So 10% of the time, people who are not infected will actually give a positive test result. So let's say that you've tested positive. Now you want to know, what's the probability that you're infected? Note that you can't even address this question with frequency statistics, right? This isn't a null hypothesis significant testing situation. You want to know the actual probability that you're infected, not whether or not that probability is statistically significant or not. Okay, so again, we can set it up as a table like this, where our two hypotheses are that we're infected or that we're not infected. And again, remember the data are that we've tested positive. And so given those data, we want to know what's the probability that we're infected or that we're not infected. So first we need to think about our prior probabilities. So what's the prior probability that we're infected? At first you might think that we have no way of having any information about that. But of course we do. The prior probability that we're infected is actually the infection rate in the population, right? Not knowing anything about your test result, we know that there's about a 1% chance that you're infected because about 1% of the population is infected. So our prior probability that you're infected is 0.01. And because our prior probabilities have to add up to 1, the prior probability that you're not infected is just going to be 1 minus 0.01, which is going to be 0.99. And again, our prior probabilities have to sum to 1. So hopefully that makes sense. So then we need to calculate the likelihoods. So this is the probability of the data given the hypothesis. So again, the data are that we've tested positive. So what's the probability of testing positive if we are infected? Okay, so that's going to be 0.8, right? 80% of the time, we're going to test positive if we are infected, right? So that's going to be 0.8. Whereas the likelihood that we're not infected, given the data that we've tested positive, is going to be this false positive rate, so 0.1, right? So again, it's the probability of the data testing positive under the hypothesis that we're not infected, right? So 10% of the time, people are going to test positive even if they're not infected. So those are our likelihoods. Now we just multiply each of these rows. And so we get 0.008 for infected, 0.099 for not infected, and then we take the sum of those, and that gives us 0.107. And so now we have all of the numbers that we need to calculate the posterior probability of each of these hypotheses. So that tells us the probability that we're infected, given the data that we tested positive, and the probability that we're not infected, given the probability that we've tested positive. So the probability that we're infected is just the product of our values here, 0.008, divided by the sum of that value across all hypotheses, so 0.107, which is 0.075. And then the probability that we're not infected, given the fact that we tested positive, is this value. Sorry, whenever I move my mouse, it shows that navigation bar shows up, so I'll have to deal with that. Anyway, 0.099 divided by 0.107, which gives us a posterior probability of 0.925. So you can see, even though we've tested positive for this test, for this infection, it's still way more likely that we're not infected than the probability that we're infected. And this is mostly due to the big difference in the prior probabilities, right? It's much more likely that we're not infected. just given that, and that the data saying that we are infective is pretty weak. And so this actually comes up all the time, right? All tests for whatever diseases or anything do have a false positive rate and a false negative rate. And you have to consider those when you're interpreting your results. And this is actually a big reason why they've changed the age at which they're recommending women get mammograms to look for breast cancer. I don't know if you guys remember this, but I don't know, my judgment of time is not very good, but I think maybe 3 or 4 years ago, Canada upped the age at which they recommend women have mammograms. They start having mammograms. And the reason is that the false positive rate of mammograms is actually pretty high. And so women were getting positive results back, like suggesting that they do have the beginnings of breast cancer, and then making pretty dramatic life decisions. But in fact, the false positive rate's so high in those tests that even after testing positive, it was more likely that they didn't have breast cancer than that they did. And so just because of those implications, they changed the recommendations to say, you know what, there's so many false positives and people are making life decisions based on those false positives that we need to change the way we do this and kind of up the age at which they're recommending mammograms to an age where it's more likely, right, where the prior probability of being infected is, or not being infected, but having breast cancer is higher, so that these false positives aren't going to be such a big issue. So again, this Bayesian statistics allows us to get a probability of a hypothesis given the data, which is often what we want. Okay, so that sounds lovely. So why don't we do this all the time? Like, why isn't this the default? It seems like it has everything. It does everything that we want. So why isn't everybody on board? So the biggest criticism of Bayesian statistics is this use of priors. So a lot of people say, you know what, we shouldn't be doing this, right? Why we shouldn't be putting this subjective judgment into our analyses. And of course, it's not always subjective, right? In the examples that we just did, our prior probabilities were informed by data, just not the data of our test. So of course, being able to include prior information is extremely useful when you have prior information, right? So if your study is one of many, right? If other people have done similar analyses, you can use the results from previous analyses as the priors for your study. And this is actually a huge strength of Bayesian statistics, right? I think the example of the car crashes, like when we were talking about our criticisms of p-values, the issue with the study on car crashes was that each state did its own study and considered its own study in isolation. And so even though every state showed an increase of crashes when they implemented the right turn on red law, in no state were those statistically significant. But if you looked at all the data together, there was a huge difference in the number of crashes, but nobody did that. So Bayesian statistics allows us to use previous studies to inform the prior probabilities of our analyses, and that's very, very powerful. And of course, null hypothesis significance testing can't do that. You can't incorporate prior information into a given test. But of course, a lot of the time, we don't have any prior information, right? That's a lot of the science that we're doing is, I don't know if I'd call it cutting edge, but it's work that people haven't done before. That's the whole reason why we're doing it. It's because we're asking new questions. So in those cases, we don't have any prior information. So what do we do in those situations? Well, there's a number of choices. What you can do is choose what are called uninformative priors. And this is when you assign an equal probability across all your possible hypotheses. Another thing you can do is choose weakly informed priors. And so these can be just priors that are very, very loosely based on the data. And we'll come back to this a little bit later. But then, of course, you can be explicit about what you really think, right? You're all experts, or you're all going to be experts in a particular field. And by definition, an expert has a better understanding of certain topics than other people, and you should use that expertise in your life, right? You use that to figure out what studies you should do, what study organisms to do, how to design your study. So you should use that expertise also to inform your prior probabilities, and that makes sense, right? We shouldn't assume that you don't know anything. So you can be explicit about what you really think is going on for your priors. And of course, one thing that we can do, and that you'll see we'll do this in this course, is you can choose multiple types of prior and make sure that you get the same posterior probability regardless of what prior you choose. So maybe I think a certain prior probability is appropriate, but maybe someone else thinks something else is appropriate. Well, what we can do is run the analyses with both and say, okay, well, you don't like my prior, but let's test it with yours. And then if we get the same posterior probability, given those different prior probabilities, then we know that our interpretation of the data is robust to whatever prior that we use. And that's, of course, useful information, right? To know that those results are robust regardless of what priors we use. So there's a lot of, to me, that criticism doesn't really stand up because there's a lot of things that we can do to make sure that our priors are appropriate, and you'll learn those as we go. So again, some people think of this requirement of including prior probabilities makes the analyses too subjective. But of course, we didn't really get into this in our criticism of p-values, but there are a huge number of subjective aspects of null hypothesis significance testing too. And these often are hidden from us though, but they're there. That doesn't mean that they're not there. So for example, there's many different ways that you can conduct a t-test, and each program, has chosen one, and they don't really tell you which one they chose, but you just assume that it's correct, and you say, oh, I haven't made any subjective decisions, but you have by choosing a certain software, and depending on what assumptions they make about a t-test. Like, not all t-tests are the same, and the same is true for any statistical test. So just some of these subjective aspects of p-values and null hypothesis significance testing are, the choice of a critical p-value, the requirement of a normal distribution, the intentions of the researchers, what test to use. There's just a whole range of subjective decisions that go into frequentist statistics as well. And so this has been well documented. This is a paper, I'm not going to assign you to read it, but if you're interested, this is just a paper that goes through kind of frequentist statistics and all the subjective components that go into it that are often hidden from the users these days because we use different statistical packages, and so those assumptions are hidden from us, but they're there regardless of whether or not we know about them. So this is a paper from the American Scientist in 1988. So that reference of information is there if you are interested. If you're interested in this paper and you cannot get a copy, just let me know and I can send it to you. So to me, I think requiring this prior information, I actually think it's a strength of Bayesian statistics, because for a number of reasons. For one, it forces us to really think about and be explicit about our assumptions, right? To define priors, you have to have really thought about what's going on and have to have really thought about what you think the relationships are between different variables and things like that. And you have to be explicit about it. Whereas all those assumptions are kind of hidden in null hypothesis significance testing. If there's debate about what priors are appropriate, again, we can use multiple priors and make everyone happy and ensure that we get the same results, right? So what could be wrong with that? So again, I think that this use of priors is a strength rather than a weakness. All right, I think we'll stop there. Actually, there's just a little bit. We'll come back. We'll stop there and then make one more video on this topic.